Hello, welcome to CSC 351, Introduction to Data Science. Today's topic is about classification, and in particular we introduce one classifier named logistic regression. So far in this course, after we introduced linear algebra and then probability and then pre-processing, now we are in a stage that we can do the statistical analysis, we can do prediction. Prediction can be performed in different ways. Mainly we have two ways to do prediction using unsupervised learning, and the other method is supervised learning. We discussed that the supervised learning can also be categorized into two groups, regression and classification. We talk in detail about linear regression and how we can map a feature space to an output which is a continuous variable. Today we will talk about classifiers, how we can design a classifier, and in particular we focus on one popular classifier known as logistic regression. So I have a brief overview again on the classification problem in machine learning and data science. So basically the goal of the classification is to find an estimate for a function which map an input which is from a domain of a vector to a categorical variable. So we would like to estimate a function called f, whose input is a vector of dimension p, and the output is a categorical variable. Could be a number, could be a string name, could be any type of object, but the characteristic of this output should be a discrete value rather than a continuous value. So therefore what we have, we usually are provided with some samples from the input and output of this model. Namely, let's say we have n samples, and each sample is presented by a pair where the first value of this pair is a scalar and the second pair is a vector. Then we usually have n samples, and also we have the features, and the dimension of feature space is usually denoted by p. And then the goal is that given this training sample, we would like to find the function f as close as possible to the actual function, and this function also should be able to predict the correct label for some new data presented to this classifier. So therefore the task of classification is training and testing. In training, we would like to find a good estimate of function f, and in the test phase we will check the performance of the classifier on unseen data to see how the classifier would perform. So let's now focus on a task of binary classification. That means the output has two outcomes. The output has only two outcomes. So if I wanted to say y basically belongs to a binary variable 0 and 1. It could be also y belongs to two words like yes and no. Or sometimes usually also y belongs to these two discrete values, -1 and +1. So the output has two discrete outcomes, 0 or 1. So therefore we are mapping a feature space of dimension x of p to a domain of two values, 0 or 1. So let's start by an example, and then I explain to you how we will solve this binary classification problem using logistic regression. So the reason in here I started by introducing logistic regression is as follows. So logistic regressions, first of all, they are very powerful classifiers, and also they can use for not only for binary classification, for also multi-label classification problem, an extension of binary logistic regression. And the other reason is they are also somehow a foundation behind the neural network. A good understanding of logistic regression helps understand a neural network, deep learning better. So consider this example that we would like to see patients are visiting a clinic, they are suffering from diabetes or not. So if they have diabetes, we just label them 0. If they don't have diabetes, we label them 0. If they have diabetes, we label them 1. And what are the features in here? The features is based on the weight and also the blood pressure of that person. We would like to see if that person has diabetes or not. So therefore, the classification problem is as follows. We have 2 inputs for each patient, so x1 and x2, and the output is y, so it could be 0 or 1, right? So let's go back to the classification problem, and for this example, see the number. So what is the number of samples we have, number of patients we have? So in here, n is equal to 400. What is p? The dimension of the feature space is 2. So therefore, p is equal to 2. So this is very useful at the beginning of each classification problem. You make sure that you understand the number of samples, the dimension of feature space, and then don't confuse these two. Otherwise, you get lost and you cannot proceed to design your classification problem. So I can also, if I put these two features together as a vector, but the vector could be x, which is x1 and x2, where the first term or first dimension denotes the weights, and the second dimension in this vector denotes the blood pressure. And the output in here is y. So in here basically y1 is equal to 0, y2 equal to 1, and y400 is equal to 1. Note that we use the superscript as the index for sample and subscript as the index to denote the feature. For instance, if I use the term x 125 2, that means the blood pressure for the patient's label 125. So distinguish between superscript and subscript. Note that in different literature they use different notation. Make sure first of all you read the convention for that work. So in here we use the superscript in order to denote the sample, and then subscript is used to denote the feature space dimension. Okay, so this is our problem. So basically this is the feature space matrix. We can use it by x, and this vector is basically the output. And then we wanted to see, can we design a function f when we present to this function a vector like xi, we could predict xj, we predict the output yj. So that's the task. What is this function? So in here, we wanted to design a function which we call it later on a logistic regression classifier. So the output of this function is either 0 or 1. So if we put these things together, then we have a vector, the output vector, or this is y, and then we have a matrix which has two vectors, vector 1 and vector 2. So vector 1 is basically the weights for the 400 patient, and vector 2 is also the blood pressure for 400 patients. So you can also consider this one as a matrix. So sometimes when you read the file, that file has 3 columns. The first column is output label, which is a binary vector usually from 0 or 1 or -1 and 1 or yes or no, and the rest of the columns represent the feature space, feature vectors. Okay, so you have x and y, and then the task is to design a function f such that this function, when you input a vector, returns 0 or 1. So the first idea may come to our mind is, can we solve this problem using regression? Because in regression, linear regression, so we have y, which is our output. So y, then I can say y equal to a0 plus a1 x1 plus a2 x2. So okay, so if can be solved using regression problem. I have the inputs, I have the outputs for label data. I can solve and then find a0, which is intercept, and then a1 and a2 are the coefficients of linear regression, and then I can estimate the output as we discussed for linear regression. But there is a problem in here. The problem is when we define the linear regression, there are some constraints that if the input vector and output vector they don't have that constraint, then we cannot solve the problem using linear regression. In here, the output is a binary value. So this output is a binary value, right? A binary value. Okay, so one of the assumption we have about the regression, linear regression, was the output follow a Gaussian distribution. And in here, the output follows a Bernoulli distribution. Bernoulli distribution is outcome is okay 0 or 1. Let's say an experiment, you just flip a coin, it's just be head or tail. This is a Bernoulli distribution. There's a probability that the output is 1, and there's a probability that its output is 0. So the output for this example of the predicting if the patient suffers from diabetes or not follow another distribution, which is a Bernoulli distribution rather than a Gaussian distribution. Therefore, we cannot attack this problem using linear regression. So therefore, we should seek another approach to solve this problem. So the first one, the researcher encountered this problem, and then they thought, can we extend somehow the linear regression and reformulate that one such that make it work for this binary problem? And note that this is also binary classification. This is, the output is not a continuous value. So what was the condition? As I said, one of the most important condition is y follow a normal distribution. Y follow a normal distribution. So can we change and somehow manipulate y such that it will become a normal distribution rather than a Bernoulli distribution? So we'll show that we can do that, and that will lead to what is called a logistic regression classifier. So can we solve this problem using a linear regression? The answer is a big no. What is the reason? The reason is y is a binary value, such we expect the y be a normal distribution. So y should follow a normal distribution with zero mean and a variance sigma, but y is a binary value. So this condition is not met, therefore we cannot solve this problem using simple linear regression. Okay, so what is the logistic regression? As I said, so one may approach this problem saying I have 400 samples. For these samples, I have a linear relationship between input and output, and then try to solve it using linear regression. But as I just discussed, we cannot solve this problem using a linear regression. So this is not possible. So if you, instead of using this binary value 0 or 1, we use a probability of an output is 1 or an output is 0, and then say this probability is linearly related to the input space, right? So in here I can say, okay, can I say the probability of y for sample j, for the jth patient, is equal to 1 given an input feature. So it's also important how to read this probability. The probability the patient number j or jth patient is a diabetic person given the input, given the weights and blood pressure for this sample, is equal to a linear relationship of the input feature. But you readily also reject this approach. The reason is we know the probability should be equal to, is bounded between 0 and 1, whereas this linear relationship, it goes from minus infinity to infinity, right? And another reason is the probability distribution is not this function is not necessarily, we know that this function is a Bernoulli, is not a Gaussian distribution. We know that this probability is not also a Gaussian distribution, but that will help. So this one also we cannot go. That will help that using a little bit of tweak, we make this probability a Gaussian, follow a Gaussian distribution, and then extend from minus infinity to infinity like a Gaussian distribution for output, and then say that output is linearly related to the input features. And then for that, we use this log of probability that y equal to 1, 1 minus 1 equal 1. So basically this, what we have in the denominator, is the probability that the sample j is 0, right? Is not diabetic, given the input features. 1 minus, because there are two outcomes, right? We know these two outcomes. We know that P1 plus P2 should be always 1. That's the fundamental of probability, and then P2 therefore is 1 minus P1. This is what we have in denominator, and this ratio is called odd of probability. This is odd, the odd of this. So you can see that this is exactly if the probability that yj equal to 1 is high, this ratio goes up. Namely, if consider this probability is 1, then this would be an infinite number, right? And then also if this is close to 0, that will go to minus infinity, so the range. And then we take the log to make it bounded. So this is now, we can say, follow a normal distribution. We can make it 0 and with the variance equal to sigma, or we can also normalize it to make it a unit variance. So this probability now is we can solve it using linear regression. So know that this is linear regression. This is linear regression. Okay, this is linear regression. But we would like to find this probability. So if you solve this problem in terms of the probability of y j equal to 1 given xj, this probability is equal to 1 over 1 plus exp. This is an exponential function. This is what it is like the function. If you have a function y, if f of x equals to exp of x, this is this function. This is natural number e to the power of x. So usually we use by exp. So x was minus. Note that we have a minus in here, and then this is a linear relationship. So this is very important to study and understand this relation, because later we will also use this one in neural networks. So then for this probability is we can also call this probability as a function called h, which has an input. Input is xj, and then a parameter. So this is a parameters in here. Parameters of this probability. So a probability has a parameters, a function has a parameters. And this is a parameter which is unknown, we would like to estimate. So this is unknown parameters. So the goal of this, as I said, the goal of a classification in training phase was to find a function as close as possible to actual function. Here we would like to find parameters of probability which is as close as to possible to actual probability, and this probability gives us the odds of that input equal to 1 or the odds that input is equal to 0. So this is called logistic regression. So this is called logistic regression function. So this is logistic regression. Logistic regression classifier. Okay, so what is the, so let's assume that we have the parameters. That means we have the A0, A1, and A2. These are the parameters of this classifier. Then if you have an input, you can easily compute the probability that this input is 0 or 1. Note that in here we don't get a deterministic value that, okay, if the input is this, the output is 0 or 1. But we get a probability that the input and output. In fact, for many of the classifiers, we don't have a deterministic output for our function. It's all about probability. So we obtain a probability, and then based on that probability, we decide that the output is 1 or 0. And then we can bring the uncertainty into our problems, and then we can make some quantification about the power of this classification, right? So therefore, if this probability of, let's say, for sample 100, given the input 100 is equal to 0.8, then I can I'm pretty much sure that this sample y100 is equal to 1. Or I can say, okay, this patient, this visitor is highly likely suffering from diabetes, or he's a diabetic person, right? So then it comes to probability, and we can put a threshold. For instance, we can say, okay, if the probability is more than 0.5, the output is 1. If less than 0.5, the output is 0. Later on, I will show you how to evaluate the performance of the classifier, what are the metrics we are using. But for now, I want you to know the concept and intuition how we obtain a logistic classifier, and what is the relationship between a logistic regression and linear regression, and why we need to make this rather complicated formula compared to logistic compared to linear regression. So now the next question you may ask, okay, now I compute the probability I found. How can I compute the parameters of these probabilities? So I have a probability, how we can compute the parameters of this probability. So we said that probability that y jth is equal to 1 given input is a function, is equal to a function which has an input vector and the parameters vector. You want to compute the parameters vector. So how to compute the parameters? In here we are using one of the most popular techniques in estimation theory and in probability. Is called the maximum likelihood estimation. Maximum likelihood estimation. So what is the maximum likelihood estimation? So in maximum likelihood estimation, we would like to obtain the parameters of a distribution, we wanted to have the sufficient statistic of a distribution or parameters of the distribution. What we have some samples from this distribution. So what basically, so let's say for a distribution we have collected some samples. So we have samples x1, x2, and all the way to xn. And also we know that these samples might be vectors, they're not scalars. So that means they might have different dimension. Each dimension is a feature space, right? So we can also say x1 vector belongs in here to Rp. That's a vector of dimension p whose elements are real numbers, okay? It shouldn't be always a real number. There could be some strings or other type of other features or integers, but for now we assume these are real numbers. So, and then we know that these samples are coming from a probability distribution. In order to be consistent with the our notation, I should use a superscript in here. So it should be one. I should delete this and then to put this one in here to be consistent with what we have. Sample 1, sample 2, sample n, and this is an arbitrary sample, sample n. Okay, so having these samples, and then we know that these are from a probability distribution of xj's given some parameters. So theta in here denotes the parameters of this distribution. It could be anything. For instance, if this population has a Gaussian distribution, the parameters are mean and variance. If this is a Poisson distribution, then the parameters is a lambda. So if it is a Laplace distribution, there's only one parameter. So it depends on the type of distribution. For our case, we know that the parameters of distribution is vector A. These are the vector A, okay? So now how we can use the maximum likelihood estimation. So maximum likelihood estimation, say, I wanted to find the parameters that they maximize the probability of seeing this data. The probability of seeing this data. So if I have n sample, then I will form this, basically the maximum likelihood estimation is finding theta, which is basically the arg max of the multiplication of these probabilities, px1 times px2. So let's keep the notation also consistent. Px1 given theta times px2 given theta times pxn given theta. Okay, so but the problem with maximum likelihood estimation is we have the product of some small term. So in here I'm multiplying n probability. So n is usually at the order of 10,000, sometimes million of samples you have collected. So if you want to multiply million value smaller than 0, this is getting very numerically not stable, and you want to have problem with the precision. So what we do, we are usually, instead of maximizing this probability and computing the theta, we compute the log of probability. So if you take the log of this probability, the product will be converted to the sum. So therefore, the maximum likelihood estimation usually is taken on log of probability is argmax of on theta, which is the probability, basically log of px1 given theta plus log of px2 given theta plus log of pxn given theta. And then I can use this sum as a compact form using sum notation. I'll get this value. So this is called the maximum likelihood estimation. As I said, this is very powerful and very common technique in the estimation theory when you have a sample from a probability distribution and you wanted to find the parameters of that probability distribution. So what we do basically for the logistic regression, as I said, we have a probability which is h. We call it h for a sample xj, and then parameter vector which is a, and then instead of using we take the log of this probability and then we find the value for a that maximizes this probability. So let's say if a is a vector, can get 100 different choices. We plug in these 100 different choices in here. The one that gives us the maximum probability is the best value for parameters that maximize the likelihood function. Note that the likelihood function is not a probability, it's a function of the parameter. So what is unknown in here is this parameters you wanted to find it. So you can consider that the likelihood is a function of parameters, and then you wanted to maximize this function. You want to find the value of parameters that maximize this function. This is called maximum likelihood estimation. Sometimes they call it MLE. If someone just say use MLE to find the parameters, that means maximum likelihood estimation. And when we talk about the maximum likelihood estimation, we mean that take the log of probability. Some texts they use the log MLE, but we barely use only MLE, without taking log, because as I said, this is difficult in terms of computation. But now we use the maximum likelihood to obtain the parameters. So okay, how to solve, so in here I have a function of so this is, I can call this one is a function j. What is the parameters is a. So how can the a that maximize this function, this is another story. So we need to find some optimization. You should apply an optimization algorithm in order to find the value that maximizes this function. So from high school, we know if you have a function and you wanted to find the value that maximizes function, you take the derivative, you set the derivative to 0, and then you solve that equation. That one gives you the maximum. But unfortunately, for many of the optimization problems, we don't have the functions are we cannot take the derivative of those functions. It's very complex. So, but fortunately, there is a very simple and effective method called the gradient descent algorithm that is used to solve this type of problem. So in fact, the gradient descent algorithm and their extension, like a stochastic gradient descent, like a batch gradient descents, like the Adam optimization techniques. They are the state-of-the-art techniques that are used in most modern and state-of-the-art classifiers like deep neural networks to obtain the parameters. So we will talk about the basic of the gradient descent and how we use to find the maximum or minimum of a function. So for now, what we need to know is, okay, how we basically form what is a logistic regression classifier, and how we get to that logistic function, what's the basic, and then how we solve for the obtaining the parameters. So the technique we are using is a maximum likelihood estimation, and then when we wanted to solve the maximum likelihood estimation, we ended up having an optimization problem. How to solve the optimization problem is using the gradient descent algorithm, or a stochastic gradient descent algorithm. We'll discuss later how to do it. So that was basically the idea behind logistic regression classifier, and by now you know one of the most popular and very effective and powerful classifiers which gives you very good performance. There are also many other classifiers. We start by the simple one like naive Bayes, like support vector machines, very popular during you know, the 2000s, and also we have the random forest classifier. We have boosting algorithms, we have decision tree classifiers, but collectively, if you wanted to pick up a very good classifier, it depends on how many samples do you have. If you're working with big data, the way to go is using neural networks and also logistic regression. They give you the best performance, for no doubt. Having said that, you should not underestimate the power of other classifiers. For instance, random forest classifier, in some cases when you don't have enough samples, they give you very good performance, and they also beat the neural networks. But as I said, in today's real problem, we have deal with problem with lots of samples, and the way to solve this problem is in neural networks, and logistic regression is basically a very simplified version of the neural networks or deep neural networks. So I will stop here, and then in the next lecture I will talk about how we can evaluate the performance of a classifier, and then we'll talk also about the gradient descent algorithm, which is a technique that used to find the parameters of an optimization problem. So I wish you all a good or night day, and see you in next video soon.